So the next speaker is Maulik Parikh, and he's talking about the noise of gravitons.
Yeah, testing. All right. All right. So I'd like to thank the organizers for this wonderfully broad conference, and also for giving me the opportunity to speak. I'm going to tell you about some results that I find very exciting. They're exciting because they give us the hope that we might see observational signatures of quantum gravity, maybe even at gravitational wave detectors that we currently have. All right. So here then is a summary of my talk. I can't see the slides from here. Here's a summary of my talk. If you have a pair of freely falling particles, then you'd expect that quantum fluctuations of space-time will induce random noise, jitters, in the geodesic deviation between those particles. And that's what we're going to find, and that's really the focus of the talk. We'll investigate that contribution of quantum fluctuations. And that noise, if you have an entire congruence of geodesics, will add a quantum term to the Raychaudhuri equation, which we'll derive. And the characteristics of the noise, the statistical properties, such as its power spectrum, its amplitude of the noise, the autocorrelation function, those all depend in a calculable way on the quantum state of gravity. I feel my sound is going in and out. Hold on. Hello? Is it? Maybe turn down the volume. In particular, we find that for a squeeze state, the noise is exponentially enhanced, and maybe in optimistic scenarios might even be observable at gravitational wave detectors. Okay, so here, just to set the stage, is what we mean by geodesic deviation. If you have two particles that are moving along geodesics, let's say they have mass m and m naught, then there's a geodesic deviation vector, which is a space-like vector that joins them, and we'll be interested in the evolution of that vector. And by the way, everything I'm going to say today is going to be about time-like geodesics. So these are massive particles. And if you like, you can think of these massive particles as two satellites of LISA, or maybe the two mirrors of LIGO, or what have you. It's a very interesting question to repeat this calculation for the null case. Okay, so classical GR tells us that the geodesic deviation equation, the geodesic deviation evolves via a geodesic deviation equation in which the Riemann tensor appears here on the right. And in the presence of a gravitational wave, a classical gravitational wave, the Riemann tensor takes this form. And so if you insert this over here, this is what you get for the geodesic deviation equation. So this is all classical. And the question naturally arises, what is the generalization of this equation when the space-time metric is treated as a quantum field? So that's what we're going to answer. And this is work so this is the question that I set out to address with my collaborators here. This is Frank Wilczek, this is George Zahariadeh, and we wrote 3 papers in 2020. The first of these won the Gravity Prize here. But then there's also a PRL and a PRD, and these are basically in order of increasing technical difficulty. So if you want to know all the technical details of the derivation, you should go to this last one here. So let me just sketch the derivation. And again, this is going to be a robust and rigorous calculation in linearized gravity, although maybe I shouldn't use words like robust and rigorous immediately following Richard Woodard. But here's the starting point. We're going to take the action for Einstein-Hilbert action, and it's just going to be coupled to 2 massive particles, and that's of course the equations that's of course the action for massive particles. And we're not really interested in the motion of the full motion. We want to make it a 1 degree of freedom. We are focusing on the separation of the two particles. So what we'll do is we'll put one of the particles, let's say the capital M, we'll put it on shell, and we'll put it at the center of our, we'll go to its center of, we'll put it at the origin, and so its position will just be this. And then the other particle is going to have this coordinate, and this deviation xi is going to be the geodesic separation, and that's a gauge invariant quantity. Okay, we can also use ferminormal coordinates attached to the first particle, and if we do so, here's the metric, and inserting that into that second particle action, this is what we get. All right, and we can also expand the Einstein-Hilbert part in metric perturbations as usual, and this is in TT gauge, and this is what we find. So this is our action for the system of interest. And here's the action again. And now what we can do is we can take these perturbations, Hij, and expand them, decompose them in Fourier modes. So here, Q sub k is the amplitude of the perturbation with momentum k. And if we do that, we find this particular action. I've put the system in a box that's why there's a discrete sum here. And I also defined some quantities here which are dimensionful. Okay, so just to show how simple this is, let's just focus on what it looks like if there's just one mode of the graviton. So here's a single mode. This is a mode. This is the amplitude Q of a gravitational mode, of a perturbation mode with frequency omega, and this is what the action would look like. Or these two terms here, that's just like a simple harmonic oscillator. Then there's a free particle, and then of course there's a coupling, and because it's gravity, the couplings are derivatives couplings, and here's what you get. There's a kind of a Yukawa type coupling, except there's a slight complication that they're derivatives. Okay. So that's the action, and it's very simple. And in particular, both fields, both degrees of freedom, especially and notably the Q degree of freedom, are no more than quadratic. So we can actually solve this exactly. We can quantize this easily because we don't have to. There's no actual cubic terms. Okay, so here's the quantization strategy. We're going to treat both the deviation, which you can think of as the position of that second particle, and gravity quantum mechanically. All right? But the deviation is actually the position of the second particle, and if you have LIGO in mind, that's really a 40-kilogram mirror. So ultimately, we're going to take some classical limit where we'll be interested in the classical equation of motion of that mirror. But we'll integrate out gravity and take a saddle point, and what we'll get is a geodesic deviation equation, but in the presence of a quantized metric. Okay? So the idea is we're going to quantize this theory, but then integrate out gravity and take the saddle point for the deviation. Okay, so let's suppose that the gravitational field is initially in some state psi. Right? This could be the vacuum state, or if there's an incoming gravitational wave, it could be a coherent state, or it could be some other state, like a thermal state or a squeeze state or whatever. Okay? And so formally, what we want to calculate is the transition probability of, so that's a probability, P, of the detector to go from some state A to some state B. And so the detector, or the deviation vector rather, so the deviation, that's also, you can also think of that as a position of the second particle. So if you like, you can think of A and B as position eigenstates. So that's like saying, what's the probability of going from here to here in a time t, okay? And in the presence of this gravitational field that was initially in this state psi. But we don't know what the final state of the field is. Why not? Because it's interacting with masses. Okay, so there's exchanging energy, and so we can't fix the final state of the field. So the best we can do in that scenario is we can't calculate probability amplitudes. because that requires fixing the final state of the field, but we can only calculate probabilities. And in so doing, we have to sum over final states of the gravitational field. So this is the object of interest. We start out with the deviation in state A and the gravitational field in state psi. We evolve forward in time using the action that we found. We want to look at the deviation in state B and the gravitational field in some state F, which we sum over. And that's a probability, not an amplitude. Okay? So this calculation can be done explicitly and exactly because of the relatively simple form of the action. We can do it either through path integrals or canonically using BCH formula. And as an aside, I want to say that this kind of calculation is part of a very general class of problems that were studied way back in the 60s by Feynman and Vernon. And so what Feynman and Vernon looked at was, supposing you have two interacting quantum systems, and you're only interested in one, maybe the other one is the environment or something. So you can, but because they're interacting, they're exchanging energies, so you can't really say what the final state of the system of the system is. So if you even have some, so if you have some initial state, you have to sum over final states of the system that you're not interested in, and then you can integrate it out. And Feynman and Vernon gave a way to integrate it out, and the result is that the entire process, the entire influence of the system that's been integrated out is encoded in some object called the influence functional, which is in general a double path integral. So that's exactly the situation we have here, because here we have two systems. We have a deviation vector, we have a deviation, and we have gravity. Those are two systems. We want to integrate out gravity and find out the influence on the deviation. So this is our expression, and there's a Feynman-Vernon influence functional that's explicitly calculable. And you can see that this is a probability, so it's written as a double path integral, not just as an amplitude. And here's the path integral, and there's a minus sign here because it's a complex conjugate, so the I will give you a minus sign. And so that's the influence functional. And this is formally what the influence functional is. There's an integration. You're integrating out the gravitational field H. And this can be done. Okay, so the details are, it's a long calculation, but it's not particularly hard. Okay, so here's the result. The result is that the answer looks like this. There's an exponent of some object in which there's something squared. Okay? It's e to the minus something squared. Now, why is that important? And that's something squared. X turns out to be the second derivative of the position of the second particle squared. Okay. So why is this interesting? Why is this particular form remarkable? It's because of this trick from Feynman and Vernon, which is really just a trick of calculus. So in calculus, whenever you have an expression like this, exponent of a square of something, you can always pretend that this is actually the result of doing an auxiliary Gaussian integral. Okay, so you can always rewrite any square of an exponent as a Gaussian integral. And what we have here, that's the exponent of a square of something, okay, but there are integrals here, so this is like many of these. And so repeating this trick an infinite number of times, what you're going to get is an auxiliary path integral, not just an auxiliary function, not an ordinary integral like this, but a whole path integral n. And the interpretation is that n, because it's in a path integral, is a random function, or in other words, noise. Okay? So whenever we get an influence function like this, it can be interpreted as noise. It's Gaussian, zero mean Gaussian stochastic noise with some autocorrelation function A. So that makes sense intuitively. You've coupled two quantum systems, and you've traced out one of them. Okay, so since quantum systems are sort of probabilistic, you can imagine that even though you are going to take the classical limit of the other one, it's coupled to something quantum, so it'll have some stochastic behavior, some noise from its coupling to that quantum field. Okay, so let me just skip this. And so finally, when we take the classical equation by taking the saddle point, here's what we get. So this is to be compared with the original equation. Remember, this was a geodesic deviation equation in the presence of perturbation H, classical perturbation H, classical gravitational wave. we now find that we have three terms on the right. Okay? We have this original term, which is any classical gravitational wave that might be there. We also have this term on the right, which is like a radiation reaction term that you might, similar to what you have in the Abraham-Lorentz force in M. But I won't have time to talk about that. But most interesting here is that we get this quantum noise. There's a stochastic noise. And this n here was precisely the n that still sticks around here. Even after we've done the path integrals over xi, we still have this extra path integral over n, and that's why there's a noise. Okay? So there's some noise function. And so that means that the equation of motion of this particle no longer becomes a classical deterministic geodesic deviation equation, but the quantum equation is actually a stochastic equation. Okay, so it's more like a Langevin equation. So this was the main result of our calculation. Okay, so let's interpret that. So if we look at the original picture, this would be a space-time diagram of two particles. So if there's an incident classical gravitational wave, then their separation will get modulated by that gravitational wave, like so, greatly exaggerated, of course. But now, because of this noise term, we're going to find that it doesn't just look like this, but there will be little random noise, little jitters, and that's you can interpret that jitters sort of heuristically as the particles being bombarded by gravitons. Okay, so this is the noise of gravitons. And incidentally, this would be true even if there weren't any classical gravitational wave present, even if the two particles were living in a vacuum or in some other state where there's no actual wave. All right, so the punchline is that the signal of quantum gravity is in the noise. And I should say that historically, the role of noise has played a very important role in physics. We had, Penzias and Wilson discovered the CMB from excess noise in their radio receivers. We discovered fractional quantum Hall effect from electron shot noise. And we, of course, discovered the discreteness of matter, the existence of molecules as noise from Brownian motion. Okay, so that's sort of similar to this. We'll hopefully we'll see the discreteness of space-time or the quantization of space-time through noise at gravitational wave detectors. I also want to say a few things here. The original idea behind looking for quantum gravity for noise as a sort of characteristic signature of quantum gravity dates back at least as far as to some early papers by Amelino Camelia. This work described here is in these papers in a set of papers that I told you about earlier. There are also some very nice papers by Kano et al. And by Beilok Hu and H.T. Cho, which are sort of rederiving these results, but maybe in different ways, and in the case of the Cho and Hu paper, very rigorously. And then there's sort of a different approach by Verlinde and Zurek, which I think Catherine's going to talk about it later today, in which they also get noise, but using sort of holographic methods rather than perturbative quantum gravity. Okay, so let me say a few more things here. The power spectrum, as I said, is exactly calculable for many classes of quantum states. We calculated for the vacuum, for thermal states, for coherent states, squeeze states. Here it is. This is the power spectrum for a vacuum. And if you have a squeeze state with some squeezing parameter r, there's this exponential enhancement. Okay, and we then estimated what that would mean for a gravitational wave detector. So if you have a detector of, so then xi becomes the separation of the mirrors of an interferometer. There might be a maximum sensitivity, omega max. So then if these are using figures for LIGO and LISA, if we just had a vacuum and we plugged in what those figures are, we get, unfortunately, and not so surprisingly, something hopelessly small. Okay, we'll never see a fluctuation, variance. Oh, sorry, there's a standard deviation of this much, and that's due to quantum gravity. It's a little bit better if there's a thermal state, but still unreachable. If there's a squeeze state, there would be an exponential enhancement. There's a paper by Hertzberg and Litter in which they looked at existing LIGO data to give a bound, I think, of around 40, I believe, on R that from the fact that we haven't seen this noise yet. However, if you look at the power spectrum, you see that it's actually divergent. The integrated power spectrum is divergent. So the fact that these figures are so small really comes about because we have upper bounds here on the sensitivity. And those upper bounds are very, very low in terms of frequencies. That, LIGO is in kilohertz. But if we could if we could have tabletop experiments in which we look at frequencies up to, I don't know, megahertz or higher, then we wouldn't see any classical signal there because there are no astrophysical sources that produce gravitational waves of that type. But we'd have a much better chance of picking up this quantum gravitational noise. Okay, so let me make some final remarks. First of all, intuitively, why is it that quantum gravity can be observable? And here I'm going to draw some lessons from electrodynamics. If you ask, how do we know that the electromagnetic field is quantized? How do we know what's the observational evidence for the quantization of E&M? Well, we have many different observed phenomena now, and here's a list of them. Photon anti-bunching, entangled photons, sub-Poissonian statistics, Compton effect, the Lamb shift, et cetera, et cetera. All of these cannot be explained from classical Maxwell theory. But what's interesting about many of these is that they're not loop effects at all. Most of them are just tree-level effects. They're tree-level effects in a state, such as, for example, an entangled photon state, that simply has no classical counterpart. Right? The classical solutions of Maxwell's equations are all correspond quantum in QED to coherent states. And as long as you're not in a coherent state, even at tree level, you can get strange effects that cannot be explained except through the quantization of the field. So that is our hope for gravity, at least the direction in this talk, that there can be potentially observable effects if the quantum state of the gravitational field is not a coherent state. And so we are not suppressed by the kinds of huge powers that you'd expect from effective field theory. So then you might say, well, why should the gravitational field be in some exotic state? Well, actually, gravity naturally produces, oops, I think I'm missing some. Well, I don't know what happened here. Okay, this slide didn't come out right. Yeah, okay, so there's some equations missing here. But if you have a field coupled to a classical source, okay, and let's say you have a linear coupling J phi, all right? Since phi is A plus A dagger, if you start out with a vacuum state and you exponentiate e to the J phi, that's like e to the phi A dagger, and that creates a coherent state. But if you have a coupling J times phi squared, then your vacuum state will evolve to e to the J A dagger squared, roughly speaking, and that's a squeeze state. And gravity naturally has couplings that are nonlinear like this, and those will be most prominent in the merger phase of black hole collisions. But I think also in inflation we can probably expect to see squeezing taking place. So there's a rather natural mechanism where wherever the nonlinearities of gravity become significant, we'll expect that even with the classical sources, will produce states that are not well described by coherent states. Okay, the last thing I want to say is what happens if you have a congruence of such particles. So we considered, so far we showed what would happen if we have a pair of particles and that they would have a stochastic fluctuation. But now let's consider a whole congruence of them This is work with Songyeon Bak, Shudipto Sarkar, and Francesco Setti. And so the volume of if I imagine a cube of these particles, and let's put a reference geodesic at the origin. And so now if I take the volume of this cube, let's just consider an area, would be the deviations from here, in the x direction, and times the deviation in the y direction of the furthest, okay, so of the furthest particle there. So if I have, here's my particle at the origin, here's a deviation to another particle in this direction, another one in this direction. If I multiply these two deviations, I'm going to get the area. If I did in 3 dimensions, I would get the volume. Okay? So the volume is just the product of the deviations. Oh, I'm having there are some technical problems with these PDFs. Okay, I don't know why this is happening. All right, well, you'll have to use your imagination. But each of these terms obeys the Langevin equation. And so I have, each of them has looks like xi times 1 plus n, where n is some random noise. But if I take a product of them, I'm going to get an n squared and an n cubed term as well in there as well. And the expectation value of the n squared terms is given by the variance of xi, which is non-zero and state dependent. And so that contributes to the volume. And so that gives you something called a quantum volume. And if you take the derivative of that, you're going to get a contribution to the Ray-Chaudhuri equation. Sorry, Laurent, you were interested in this, but my slides disappeared. Okay, at least my summaries are. No, even these are missing. All right, I don't know what. Okay, so here's a summary of my talk. These are the same statements I had earlier, but now with some equations filled in. The quantum fluctuations of space-time induce noise in the deviation of particles. You don't just have this, but you also have a fluctuation. The noise adds a quantum term to the Ray-Chaudhuri equation. Okay. Maybe I can upload the correct slides later. And the character. Yeah, I created them with Keynote, so maybe there was some platform problem. So the characteristics of the noise depend on the quantum state of gravity, and for squeezing, there's an enhanced noise which might be observable at tabletop experiments. Thank you.
We are running late, so I can allow only one question.
I'm happy to ask the question. So you showed that if the arm distance of this detector goes small, you integrate more, so the noise increases, right?
Yes.
So what if I go to atomic size? How much does an electron wiggle when it goes around from gravitational noise? So extremely small.
That's an interesting question. I mean, of course, so our cutoff is given by the cutoffs we put in are due to detector sensitivity, but inherently another way the cutoff enters is that we use a dipole approximation, which is to say that the perturbation is the same at this on one particle as on the other one. That means putting a cutoff on the scales of the fluctuation. That's a UV cutoff. So if I bring them very, very close together, then I should see large fluctuations. Yeah. At an atomic scale, I think it would be still pretty small if I don't change a state. Yeah.
Okay, let's thank the speaker again.
But it's a good question.